Okay, great. So it's a pleasure today to have Jens Bardarson from KTH. So he will tell us about timeline evolution of local information, thermalization dynamics of local observables. So Jens, please go ahead.
Thanks, Latko. Yeah, so I'm gonna tell you about this work that we put on arXiv, I guess last week. It's a work with two postdocs, Thomas Klein Corning, who is at UC Berkeley at the moment, and Loic Hervaux, who was here at KTH, is now in Lausanne. So this work has largely been done by Thomas. So he deserves a lot of the credit for this work. But I like the work, so I'll tell you about it. So it's basically a talk about simulating many-body quantum dynamics in systems, in closed quantum systems undergoing thermalization. And just to have something concrete in mind, I pick out here one experiment where in cold atoms, where you prepare some initial state. In this case, it's some kind of charge density wave. And then you have some Hamiltonian, and you evolve from this initial state for some time, and then eventually read out. And if you wait long enough, if your readout is at long enough time, then generally you expect to reach some kind of thermal state. So in this particular case, you would have the charge density wave, which means that there is a density on even sides and no density on odd sides. But at long times, you will have a uniform density throughout your system. And if one likes, one can think about this as being some kind of a global quantum quench, where the initial state is the ground state of some Hamiltonian, H0, and then at time t equal to 0, you switch from H0 to the Hamiltonian of interest, and then the time evolution happens with that Hamiltonian starting from this state. But one doesn't really have to think about it as a quench in that sense. One can just think about the experimental protocol of generating some initial state. But usually these initial states are somehow states with low entanglement. And as you evolve, generally you go towards states with large entanglement. And what happens here, for example, I'm looking at, or they measured the number of particles on the odd sides. So since the charge density wave was on the even sides, in the beginning there are no particles on the odd sides. But you have some, dynamics, and then settles at the thermal value. And we can do numerics, or actually not we, but whoever was doing the numerics in this work. And the numerics, you can follow the dynamics pretty well, but there's always some time beyond which most numerical methods break down. So you cannot actually go much further. I mean, this is 2012, so I suppose nowadays you can go a little bit longer, but it's still hard, at least in exact dynamics, to go to any time that you would like to go to. And the reason for this really is the fact that there is a lot of entanglement being built up, and most kind of numerical techniques are either exact diagonalization, which of course doesn't care about entanglement, but they care about size, or it's somehow methods that are based on low entanglement states, matrix polar states, for example, in 1D. So just to define entanglement, basically suppose you have some subspace A, and you define the reduced density matrix on the subspace by tracing out the rest, the degrees of freedom in the supplement of A. Then the entanglement between A and A bar, the von Neumann entanglement entropy, is minus trace of rho log rho. And this evolves with time, and this density matrix here is just psi, so it's a pure density matrix. And it's a fact that this entanglement usually grows with some power law. In 1D and diffusive system, it grows like temperature. So here's some generic system that's diffusive. There's entanglement as a function of time, and you see this linear growth. And these are finite system simulations, so you saturate at long times, but that's just because of finite systems. If it was infinite, you would just keep following this entanglement growth here. And now if you are modeling your dynamics, so your wave function, if you're capturing a wave function as a matrix product state, then the bond dimension or the size of the matrices in that matrix product state grows like e to the entanglement entropy. So the bond dimension here would be growing exponentially in time. So, and it's this growth of entanglement that makes it very hard to do dynamics to very large times. And that's the reason why, even if you improve your simulations maybe a little bit or even a lot, you get much better computers, you're not going to be able to push this without any kind of algorithmic development to very large times, but you'll go maybe a little bit further. But if you look at this curve, at least, you could say, well, but it looks like the numerics has captured all the important stuff, and all that you're missing is just some small vehicles around some constant value, and the state that you go into here is somehow a simple, not very complicated state in a sense, and this is true to some extent. If I start with an initial state which has a lot of energy, then I expect to thermalize somehow at very high temperature, let's say here. So if I'm at infinite temperature at long times here, then I can write down a density matrix, a thermal density matrix that describes the state of the system. And at infinite temperature, that's just identity. Now there is a way of writing identity in terms of a pure state by introducing some auxiliary degrees of freedom, where I just write this identity as a trace over some auxiliary degrees of freedom of a pure state which I'm calling psi 0. And in the case of infinite temperature, this psi 0 is a simple state. I can, for example, take this one, so these are my physical degrees of freedom, that are these points. And I've introduced one auxiliary degree of freedom for every physical degree of freedom. And I just put on every side I just put the physical degree of freedom and the auxiliary degree of freedom into a singlet state. And this reproduces the infinite temperature density matrix. So in terms of this pure state, this is a state which has very low entanglement. So it's a very simple state in that sense. So it's a low entanglement state here at infinite temperature. But it's not quite as innocent as it looks. Namely, if I now want to do some dynamics around this state, or even with this state, suppose I take this psi 0 here and I evolve it in time. So I just do this. I evolve psi 0 in time. Of course, if I do this, then the density matrix doesn't change because it's just identity, and rho of t for any Hamiltonian is just e to the minus i8 times identity times e to the i8. But since we have identity, it remains the identity at all times. But what happens as I time evolve is this enlarged state, or this purification of the density matrix, is that I just see increase of entanglement. So this is a bond dimension as a function of time. So even if I don't do anything, I just time evolve it using, let's say, some matrix product algorithm, the entanglement blows up. So, but in this particular case where I'm just evolving the identity, I can actually fix this, and I can fix it by doing some unitary transformation on the auxiliary degrees of freedom. And since I'm tracing over these degrees of freedom to get the physical density matrix, this u of q I can move around, and it doesn't change anything. But it does change the entanglement build up in this pure state, or in this purification of this density matrix. So if I do this, I have this extra unitary evolution here. I can evolve. I can do the simple task of evolving identity for all times. I mean, this is the minimum thing I would want to do, and that works pretty well. But of course, I'm not exactly at this state here, infinite temperature state. And if I think about trying to capture the dynamics before I reach that state, I can also think about time evolving backwards in time and seeing how the entanglement evolves if I do some non-trivial things to this density matrix. And actually the entanglement also grows then in a way that makes it makes also here in this thermal state, even if it looks simple, I also have the problem that the entanglement grows in time in such a way that I can only evolve over short times. I could try to find some clever ways of minimizing the entanglement of the purification, namely the going from this density matrix to the pure state. So there's some this unitary that I talked about. I could try to find the best way to minimize it, and one way is to minimize entanglement, which we did in this work here. And you can improve things a little bit. So there's a lot of details here, but all I want you to get is that you can improve things. So here we're going with no disentangler, going down here to something where we kind of take care of this entanglement in this pure state, but it's still the case that the entanglement grows with time. So I cannot, if I do a non-trivial time evolution, for example, here I've taken just the infinite temperature state and flipped one spin and looked at the time evolution of that state. There's still, of course, growth of entanglement, and I cannot time evolve for very long times. So that's really the message of this thing. So this suggests that there is some kind of an entanglement barrier to doing closed exact dynamics in a closed quantum system. So there is the blue line here, which was the actual pure state dynamics, and I argue that the entanglement grows exponentially there. And then even if I go to a state which is somehow an infinite temperature state and is a simple state, the way I will approach that state is through a higher entanglement state, and there's no way of getting around this. So somehow if I start from a low entangled state and I want to go to large times to a thermal state, there is this what I could call an entanglement barrier, which makes things hard and generally makes it so that any simulation of such dynamics breaks down at some time. So the question really that I want to address in this talk is can I go through this entanglement barrier somehow in a clever way? So can I go from the low entangled state to the thermal state in such a way that I keep all the relevant physical information and don't lose any important information? And I'm sorry I didn't put a list of all the people that have worked on this problem. There's a long list, and I didn't want to pick out just a few. So I just referred to the references in our papers on this. There are many attempts at doing this. We had one attempt by just doing brute force, which is just to say, well, let's do something like time-dependent variational principle, which is essentially saying, okay, I just want to take a matrix product state as my wave function, but limit the size of the bond dimension, but I want to do the time evolution in such a way that I conserve the energy. So I just say, go through this, but make sure that you conserve the energy and see what you get. And that works pretty well, but there are some problems with it. Here I show this mixed field Ising model, and starting from flipping one spin again, and we can kind of get the hydrodynamic tails, and it looks well. But there are other things where this brute force kind of doesn't work very well, and also it's kind of uncontrolled in some ways. So I would like to kind of go beyond brute forcing it and try to have a little bit more control of what is going on in the many-body dynamics. So for that, it's good to understand a little bit better how states thermalize, and the general description that we have of how closed many-body system thermalizes through the eigenstate thermalization hypothesis, which says that, well, it's true that the density matrix here is somehow thermal, but it's thermal in the following sense. It's not the global density matrix that's thermal. It cannot be, because the density matrix under unitary time evolution remains pure at all times. But a thermal density matrix is, of course, mixed. So this state cannot thermalize. There's no sense in which the state thermalizes. But observables can thermalize. Namely, the expectation values of local operators at long times can become essentially thermal. And in terms of reduced density matrices then, so suppose I want to take the density matrix which is on the support of this operator. I get that by just tracing out the rest of the degrees of freedom as before. And we sometimes write that if these expectation values become thermal, that's essentially equivalent to saying that this reduced density matrix is essentially the thermal density matrix. But it's essential that I somehow did this tracing out of this pure state, because this pure state is not the one that thermalizes. So how does this work? Well, it basically is a statement of some kind of quantum typicality. Namely, if I look at this expectation value and I expand in the energy eigenbasis, then I will have this oscillating term here, and if there are no degeneracies in the spectrum, then basically these oscillations will be fast, and I will get roughly only the diagonal terms. But even here there is still some information about the initial state. But if this matrix element, which is the matrix element of the local operator, is basically independent of which state I pick, and it only depends on the energy, and the distribution of the initial state in energy is narrow enough, then I can just take this out of the sum, and I get an expectation value of the operator which is independent of the state. So that's how the eigenstate thermalization hypothesis works. And what I take from this is really, since presumably every eigenstate will have slightly different entanglement structure, but it doesn't matter which eigenstate I take. Basically all of them give the same expectation value of local observables. It tells me that detailed entanglement structure is not important. It is important that I do have a lot of entanglement, because the reduced density matrix can only become a thermal density matrix if I have volume law entanglement. So I need to have a lot of entanglement, but the exact details of the entanglement are not so important. So during this dynamics then, there is the buildup of entanglement, but most of that entanglement isn't important. Or rather, it's important, it's there, but the details of what it is not so important. So this, of course, happens also in classical systems, where there's flow of information from relevant to irrelevant degrees of freedom. And what I want to understand now is more a little bit about this flow of information. Because that's really what matters now, is that how does this flow happen, and once I know how it happens, can I learn something? So let me digress a little bit into classical mechanics, because I kind of like the analogy to Boltzmann equation here. So if I think about a closed classical system, and I try to understand thermalization in classical systems, or rather the second law of thermodynamics, so I can think of information in some distribution of particles. And I can define the Zenon entropy, which is basically defined as this. It's minus the integral of dx px log of px. And this somehow measures the amount of information that I can extract from this probability distribution. And now I can just pick some probability density to use in the Zenon entropy. For example, I could pick the n particle probability density, which is the probability that I have particle 1 at position x1 with momentum p1, particle 2 is at position x2 with momentum p2, and so on. And then I just define this S of rho, which is then the entropy corresponding to this distribution of the particles. And I now just have to integrate over all the variables of this rho log rho. If I do this and then I ask how does this entropy change in time, I find that it doesn't change. And the reason it doesn't change, of course, is that if I have the n particle probability density and I have n particles, then I know everything that there is to know about the system. So, and if I follow the dynamics of these particles, I will at all times know the density, this probability density exactly, and there's no change in the information that I have access to. But of course, this is not what we do in classical mechanics, because this is too much information. We have no hope of knowing this probability density. So what we do instead is we say, well, I actually only care about the one particle probability density, which is then the density of particles at position r with momentum p, and I obtain that just by integrating out all but one particle from the n particle density. And then I can define this entropy here, which is now f log f, integrated over phase space. And this satisfies the second law of thermodynamics and Boltzmann eighth theorem and so on. And once I know this, I can obtain any local observables, like current, for example, just by integrating p times this one particle probability density. And this is completely analogous to kind of what I explained in the quantum case, where this rho here is kind of analogous to the full state. If I keep track of the full state, then that's a pure state at all times, and the entropy doesn't change. This is like the reduced density matrix in some sense, and this is the entanglement of that reduced density matrix. So what happens now once I have this thing, it's not of course enough just to have this probability density. I also have to know how it evolves in time, and that's of course given by the Boltzmann equation. And it has some streaming terms, it's just a Poisson bracket, and then some collision integral. But the collision integral, of course, depends on the two particle density, because the momentum here changes, for example, by having two particles colliding and taking, P1, P2 into P1 prime and P2 prime. So that means that this collision integral somewhat depends on F2, which is the joint probability density of having a particle at some position with momentum P1 and P2. So now this equation is not closed. I could close it by trying to write down an equation for F2, a time evolution equation for F2. But then I, of course, will get a collision term for F2, which will depend on F3, which is the three particle density, and so on. So I have to put in some approximation to kind of close this equation here, and this is the assumption of molecular chaos, which basically says, well, that the two particle probability density just before a collision, I'm going to assume I've lost all information about correlations between the two incoming particles, and therefore this joint probability density is just the product of the two single particle densities. And once I do that, then the equation closes, and I have the Boltzmann equation, and everything works. So I now want to kind of ask similar questions in the quantum case, namely where and on what scale is information in a given state, and I want to find a way of organizing this information such that it's useful to understand. And through this, I'm going to introduce what we call the information lattice. And then once I have this way of organizing the information, I want to understand how does information flow within this information lattice in generic dynamics. And then with those first two parts, if I understand somehow the generic behavior of the information flow, can I use it somehow to find ways of constructing efficient algorithms for direct time evolution of local information. But efficient algorithms that are not exact, because the entanglement barrier, I argued, means that we cannot make exact dynamics, but also what the point of kind of the comparison with the Boltzmann equation is a little bit that I don't really care about all the exact information, because a lot of the information goes into kind of long range entanglement, which is not important and that I don't care about, at least if I'm interested in local observables. Okay, so what I'm going to do, and I'm going to focus on 1D from now just to make things a little bit simpler, is that I'm going to introduce what I call the L local information, which is just a set of all density matrices of size L, or rather it's a set of all density matrices on neighborhoods of size L, and I define neighborhoods here as continuous sets. So for example, N52 is centered on 5 and has a diameter of 2, and so on. And of course, if I have, let's say if I have nearest neighbor interactions, then if I want to now know the time evolution of this L local information, it will depend on the L+1 local information. So basically, suppose I know the L local information, that means that I know all expectation value of all operators which have support of L or less. So if I want to know time evolution of local operators, I need to know the time evolution of this state. But as I see, just as in the Boltzmann equation, the time evolution of this generates information on larger scales. So this doesn't kind of close, and I have to find a way of closing this equation in a way that allows me to time evolution. So I basically want to ask the question, can I replace this right-hand side, which generally depends on the information on larger scale, by some function of the information that I already have only on the small scale? And if I can do that, if I can replace this by this, then the set of equation closes, and I have a time evolution for the L local information. And of course I want to do this in a way where I keep track of the information that's important. But I will have to make some approximation here, and the approximation I will want to make is one where what I don't keep track of is somehow not important. Now, this will not work always, of course, and it for example, will definitely not work if there is some information that is at long range that can come back to the short scale and I'm interested in that short scale information. Sorry? Was there a question?
Doesn't look like it.
Okay. So, for example, if there are some non-abelian onions, then of course the information about these onions is encoded on long scales. And if I do some braiding, let's say, and then I bring some onions back together to get some information about the braiding, I would lose that in doing time evolution like this. But for non-abelian onions, it's possible to keep track of the local information, supplemented just by the state of the n onions that you have. But of course, the information in the n onions will still grow exponentially in the number of onions. But okay. So I'm not going to try to solve this.
How about an even simpler example? So you've shown that mixed field Ising model, right? So does it matter whether you think in terms of spins or fermions in that case?
We have only thought about it in terms of spins. I don't think it matters, but you're thinking about whether the information
because
that
it's
have
really
a product
kind of interacting
state.
in terms of interacting in terms of fermion degrees of freedom in a sense.
Yes.
So if you ask what is this, one particle density matrix, I would rather take be the fermionic one.
Yes.
I'm not sure if it changes it.
I don't think it changes anything. We have done the simulations in the spin language, but I don't think it changes anything. I'm fairly sure it doesn't change anything. I mean, the only thing that could... No, I don't think it changes anything. Or do you have any reason you think it will change anything?
I don't have any strong reason to think it will change, but a priori it's, I mean, there seems to be some kind of basis sensitivity in principle.
Yeah, I don't think I see what you're saying, but I don't think that would be. It could affect the value of L that you will have to take in order to get what you want, but you can improve it by optimizing the basis, but the fundamental kind of problem, I don't see a fundamental problem, but I agree that you can optimize it by a careful choice of basis. So you can optimize the L that you need, let's say, to get reliable results. But there may be something I'm missing here, but I don't think so. But yeah, there will definitely be a basis dependence in a sense. Yeah, it's okay. That's not okay. So a few quantum information concepts. So I'm going to define the von Neumann information as just the log of the dimension of rho A minus the entanglement entropy, and this is essentially the number of bits that you can obtain from measurements given that you have rho A. So for example, if you have a singlet, then this is log 2, and if you and this would be log 2, and if you take one side of the singlet, but there's no information to be obtained from locally from one spin in a singlet, so this gives you 0 in that case, which is what you expect. Well, if I take the full singlet, then rho A is just well, the entanglement of the full singlet on the 2 side is 0, and then I get log 2. And then I'm going to need the conditional mutual information, which is just, suppose I have 2 regions A and B, then the mutual information or conditional mutual information is the information that's in the union that I cannot get separately from either A or B. And this is useful sometimes. For example, if I want to know what's the difference between 2 density matrices that are the same on A and on B, but they may be different on A and B, and then this is bounded by the mutual information of the 2 density matrices. And if the mutual information is 0, then I can actually recover the density matrix on the union from the density matrix of A and B separately. And this is one way to do it. This is called a Petz recovery map. And there are many of these, but this is one of them, and this one is a nice one because if this bounds in the trace norm the approximation of a density matrix on a union given the density matrix on the A and B separately. And the reason I'm introducing this is that somehow this is like the density matrices on the smaller scales, and this is the density matrix on the larger scale. And if I have a way of constructing the density matrix on the larger scale from those of the smaller scale, then that can be useful. So now I want to take a state, and I want to decompose the total information in the state in some way, and I'm going to do it as follows. I'm just going to say it's a sum of the von Neumann information on different scales. And I start by scale 0, and that's just the information, von Neumann information for a single side density matrix. Then I go to L equals to 1, and I say the information on L equals to 1 is the mutual information in this state which cannot be obtained from either of the sides below it. So it's the information that's on scale L equals to 1 that I cannot get from scale L equal to 0. And then I continue, and then at some larger scale, I define the information on this side as the information that cannot be obtained from any smaller scale. So I'm now, what I've done here is I've kind of introduced what I call the information lattice, which starts from the physical lattice, but there's an additional degree of freedom. And as I go into the information lattice in this direction, I get to information which is contained in larger and larger scales. So here the information is on scale L, this is on scale L0. And basically it works like this. So here, for example, is what I said. If I have this side, then the information in that side can actually be obtained from summing over all these the information on all these different sides. But if the information on this side is 0, so on these red curves or red dots, the information is 0. What that means is that I can actually construct the density matrix on the scale from just knowing the density matrices on the smaller scales. So, yeah. And then the second thing that this allows me to do is to define information currents, because now I've distributed the information somehow on this information lattice, which is the physical lattice plus a length scale, so it's a semi-infinite lattice. I can define currents within this lattice as just being the time derivative or the objects give the time derivative of the local information on a given site. And if I have nearest neighbor Hamiltonian, then the currents will only flow on this triangular nearest neighbors. And then then I have local currents, these are the local currents, but I can define global currents on a given scale by just summing over all sides of these local currents from one scale to the next. So if I sum over, let's say, all n here, I can get the total current flowing from one scale to the next. So that's the total current. So this is the way we want to kind of divide the information on this new lattice and look at how information flows in a state during quantum evolution. So now I'm taking this mixed field Ising model again. So it's SC, and then there are two fields, one pointing in the Z direction and one pointing in the X direction. And by taking the mixed field Ising, we're basically breaking all conservations here. So there are no, it's an ergodic model. And I'm going to look first at a simple initial state, which is just this thermal state, product state or thermal state on every site. Where on every site, it's spin up with probability 2/3 and spin down with probability 1/3. And now I'm plotting here the current or information on scale L divided by the maximum information on scale L as a function of scale and as a function of time. And for the small time, so this is t equals to 3, most of the information is here on small scales and not on long scales. But as time evolves, there is this peak that travels towards larger scales, and this essentially travels with some kind of Lieb-Robinson velocity towards the large scales. But what is interesting in this particular case is that there is a hump at low scales which remains, and it becomes stable at long enough times, and this is the stuff that contains all the local information in the state. And actually the information goes to 0 basically in between here, which means that there's some length scale beyond which there's just, you separate local information from long range information. So in this particular case, there's a separation between small scale entanglement and or short range entanglement and long range entanglement. And this is just showing on a color plot the information current. So maybe I should have shown this first. So it's you can see this hump here moving with a constant velocity to larger scales, but there's this remaining information at small scales. And I can look at the currents now, and the currents, of course, move also to larger scales. Since this becomes stable very quickly, there's no current here at the short scales. So this kind of separation of scales means that I could describe at long enough times, I can describe the state at small times by what we call the L-local Gibbs state, which is basically a Gaussian state with some operator which is local, and it only acts on some L which is small enough that all the local information is captured. And this can be done because you only have this local information, then the density matrix can be described like this. But that's a special initial state, and it doesn't always happen that you have this short scale information hub that remains. And here what we do is we take an initial state. It's the same Hamiltonian but a different initial state where this is basically identity matrix everywhere except for one side where we initialize it to be spin up in the x direction. And what happens in this case is now this is the current. There's still this hump that flows to large scales, but instead of the current going to zero at small scales, there is this tail from small scales to large scales, which means that there is a constant flow of information from the small scales to the large scales, and I cannot fully kind of get rid of this flow of information. So here's the current at scale L divided by the current at scale 1, and you see that it doesn't go to zero as it did in the other case. It kind of, you have this constant flow of information, constant information flow on any scale. And at long enough times, it seems that this current basically becomes a constant. Constant as a function of scale. So now the question is, in the first case, it was quite simple to find a way of dealing with the local information. It's just this Gaussian state that I need to keep track of. So, I mean, I could design an algorithm that keeps track of that, but it would basically be equivalent to TBD or something like that, some matrix Border state. But now the question is, how do I deal with this constant current of information? And let me, before I go into the details, let me basically say how I think about this. So basically what I want to now do is I can see that there is this flow in this information lattice from small scales to large scales. So I cannot kind of get rid of this flow. It's constantly there. But what I do when I take only L local information is that I'm throwing away some sides beyond some maximum L. So really the question is, what is the boundary condition that I should put on the scale where I cut off my information? And usually if you just do some random cutoff in a matrix Border state or something, it would be more or less equivalent to taking boundary conditions where you put the current to zero at the boundary. But then you will have the problem that if you have a constant current going from small scales to large scales, that either you will have a pile up of information at the boundary, or you might even get some bouncing back, which would start to affect things. So basically what I want to do is I want to put a boundary condition at this scale which keeps the current going. So I'm just going to, instead of saying the information is zero, I want to say the current flow is constant. So that's going to be my boundary conditions. and that's what will allow me to write down. So it will allow me to approximate this right-hand side. So I mentioned this before. I want to find a way of having this right-hand side only depending on the L local information and not on the L plus 1. Now the reason I get L plus 1, of course, is that if I take a reduced density matrix and I ask what is the time derivative of this reduced density matrix, well, it's just the commutator of the Hamiltonian with rho, and now traced over the complement of this neighborhood here. So this will contain terms like this. So this is the rho and then the Hamiltonian. But the reason I get L plus 1 is because there will be some states where I have my original neighborhood here, but the Hamiltonian will overlap with the neighborhood plus one side on outside of the neighborhood. So that's why I need L plus 1. Okay. So now I want to approximate this right-hand side by some function of rho L. And I want to do this in a way, first of all, which is compatible with this thing. And compatibility means the following. It means that there exists density matrix at scale L plus 1, which is such that this expectation value is the same as if I had used the real function here obtained from just the equation of motions with this rho tilde. And what this means is basically that the local information will remain the same, and it means that all local observables are conserved the right way. Okay, so now there are two things. If you have the case where there's the finite thermalization time, then I can just write this L plus 1 state as some Gibbs state. And then this function psi is just the convolution of this Gibbs state plus this map here. Or I can use some kind of a Petz recovery map to construct from rho L. I can construct the L plus 1 state and then I map it to get the time derivative. But in the second case where we have this current, I need something more. This is not sufficient. And what we're going to say now is that we saw that the current was essentially constant after I go to large enough scale. So I'm just going to demand that this function psi is such that I get a constant flow of information. And this is one way of doing it. It's just say, okay, I'm going to take the flow of information at scale L plus 1 to be the ratio of the information at L and L minus 1 times the current at scale L minus 1. So this condition is just coming from saying that at the boundary my flow is constant, so I have this. So with this thing together with the compatibility, I can write now down an equation for this matrix here, so I get a closed set of equations. Now there's some detail here, which is that okay, actually these two conditions are not sufficient to constrain this equation, so this function. So to fully constrain it, we just minimize the total information. That's kind of a maximum chaos type of assumption. Okay, so I should finish now in a couple of minutes. So basically, I want to show you quickly numerical simulations with these methods to show that it works, and then I'll finish on time. So now taking the same mixed field Ising model with this initial spin state pointing up, and we're calculating this diffusion coefficient. And what we see is that there's a very quick convergence of the diffusion coefficient, and we can, at not too large scales, we can get below 1%. And also we can look at spin expectation value on the central side, and we can get these diffusion tail at long times. And these are simulations that are not very hard. I mean, this is on a single laptops. You can do this in finite time. So it works pretty well. But I'm out of time, so let me summarize. So basically what I've discussed is that there is a lot of information in a quantum state, but most of this information is not important if I'm only interested in somehow local observables. But the question really is, how do I distinguish between important information or important entanglement and entanglement that's not important? And one way to follow this is to follow the information on this information lattice, and then we need then the proper boundary conditions to make sure that we have the right flow of information, and this we can do as I explained, and it works pretty well. And the nice thing about this is also that it's just based on this flow of information and local density matrices, and therefore in principle it should work also in higher dimensions. One could easily add disorder, look at localization physics, even look at dissipation. The boundary condition that we took was the simplest we could think of, but I'm fairly certain you can improve the boundary conditions significantly and so on and improve this. So I think there is a lot of things to look at here. So with that, I'll thank you for your attention.
Okay, great. Thanks a lot. So do we have any questions for Jens?
Okay, could you comment on the complexity of the objects that appear in these equations that you've written down? I mean, we're writing down one equation, but the size of them is probably equivalent to something exponential in L scalar equations.
Yeah, let's see, I guess I think we basically just need something which would be cubed in the size of the biggest density matrices. So that would be what is it, 2 to the 3L or something like that. But yeah, I'm not sure if there is anything that I mean there are some. Okay, I haven't looked, or I don't remember. Okay, I guess that this minimizing part is kind of iterative thing. So, but that usually converges relatively quickly. But the scaling of it would be depending on how you implement it. Some power of the size of the reduced density matrix. Does that answer your question?
Okay, so if I were to use this in the way that it's probably not intended, where you're trying to do things exactly, it seems like you would need to do much more work than you would have to do with an equivalent MPS method. So if you want to sort of cover things at a certain distance, the MPS, you need to have enough entanglement to sort of represent like an arbitrary vector over that scale, whereas now I need to represent an arbitrary density matrix over that scale.
Well, so sure. I mean, certainly the matrix Porter state methods are optimized to be very efficient, and I'm fairly sure in that case, I'm fairly sure you can also rewrite this in terms of matrix Porter states. The complicated part, certainly in this part, this finite thermalization time, which is more or less the case that which is exact. So that you can do with matrix Porter states exactly, because you can map this to a matrix Porter state and it's no problem. Now it would be interesting. We haven't thought about this yet, but I think it's interesting to think about what is this. Can I write this boundary condition also in terms of matrix Porter states? But yeah, sure. I mean, the matrix Porter states are efficient for a reason, right?
Yeah. Okay, so it's maybe the matrix Porter states are more efficient, but doing like this, you have some kind of like physical input on what exactly you get once the thing becomes approximate.
Exactly. So I mean, it's really this part here where you have the kind of way of writing the boundary condition that somehow keeps the information flow right, and it's not out of the question that one can write that in matrix product language. I don't really see any fundamental reason why you couldn't do that. But it's for us it was easier to formulate this thing and kind of the separation of entanglement in terms of the local density matrices. But I could, of course, at every step, certainly I could at every step take the local density matrices and write them as matrix product states, and then I will have a matrix product state algorithm. It's certainly, I mean, but then comes maybe this part, because I wouldn't know how to do that maybe as obviously in higher dimensions, but at least conceptually I don't see any problem of extending what we did to higher dimensions. I mean, we've done a little bit of work in that direction, but it gets more tedious, but there's no, so far I haven't found a conceptual problem there. No, but sure, if you are in times which what we call a finite thermalization time, then matrix product state will work just as well. Probably better.
Any other questions?
Maybe going back to the different kinds of locality between like fermionic and spin systems. It doesn't sit like you could say that it's only the odd fermionic operators which will have differing locality. Right. Well, if you're interpreting locality as like compact intervals, then if you have a even fermionic operator, then the spin operator is just as local. So it's only the odd ones, and then often for some reason we say that the odd ones aren't really physical anyway as observables. So maybe this means that you don't really need to think about fermionic systems.
Yeah, that's a good point.
It's already solved.
Yeah. Yeah, if you think about it that way, that you're, well, okay. The question is, do I need the? No, I think you're right. Probably.
Physically, you should only really get odd observables if you've coupled the system to something else.
Right.
And then maybe you say that that's out of scope as not really being a closed system anymore.
Well, I would in principle one could think about whether you could add at least local dissipation, but of course if the dissipation is not local, yeah, then it's out of scope. But if it's local, one can think of it as some kind of local sink and source in the information lattice somewhere. I haven't fully thought about how that works, but I think it should work. No, but thanks. I agree with. I think that's a good argument for fermions versus spin.
All right. Any other questions for Jens? Well, if not, I'm gonna stop the recording and close this